Sorry.
It's okay. You can just start now.
Okay, does anyone have an answer for this question? You can just shout it out or put it in the chat or something. Yeah, so those of you that said D and E are correct, because remember, for a limit to exist, it has to exist from the left-hand side and the right-hand side. So if you plug in x equals 3 into this function, you do get 0, right? Sorry, if you plug in x equals 3 into the function, you do get f of x is equal to 0. But the answer is D and E, because if you approach the limit from the left-hand side, then you get 0. But there's no function to the right of x equals 3. So it can't be, it can't exist, because in order for a limit to exist again, it needs to exist from the left-hand side and the right-hand side. And so this will show up a lot in FAMAT. Like, they try to troll you a lot by putting like square roots or like semicircles or something. So especially make sure you watch out for these like square root of like x, like square root of x functions, because test writers try to like trip you up and like make you say 0 when it's D and E, because it needs to exist from the left hand and right hand side. So yeah, so that's the existence of limits. Now let's go on to some limit properties. So we now know conceptually what a limit is, but now we're going to go more into like how to evaluate all these different limits, because when you're in FAMAT, that's majority of the time what the questions are asking. So the first property of a limit is that, so before I start, so C and K are constants, and f and x and g of x, f of x and g of x are functions, and I'm going to say that the limit of x approaches a of f of x exists. So again, that means that the limit exists from the left-hand side and the right-hand side, so we can say that the limit exists. So the first limit property is that we say that the limit is a linear operator, which is just fancy speak for it. You can distribute the limit inside of like a plus or minus, and you can distribute it like to the function itself. So what that looks like is, so for example, if I'm evaluating the limit as x approaches 2 of 2x squared plus 3x, what I can do is I can pull the 2 out and say it's 2 times the limit as x approaches 2 of x squared plus 3 times the limit as x approaches 2 of x. And so this is just 4, because you can just plug this in the scenario, and this is just 2. So 2 times 4 plus 3 times 2, 8 plus 6 is 14. So that's the first property. The second property, this one, honestly, I even still forget this property, and like when I use it, I think it's like magic. But if the limit as x approaches a of f of x exists, and also the limit as x approaches a of g of x exists, then you can again distribute this limit so that it's the limit as x approaches a of f of x times the limit as x approaches a of g of x. And so you can again distribute this limit inside of this whole like multiplication thing that's going on. One example that I can do is the limit as x approaches 0 of x times cosine of x. So this is going to be equal to the limit as x approaches 0 of x times the limit as x approaches 0 of cosine of x. And so this is going to be 0 times 1, which is just 0. The last property that we're going to go over is that the limit as x approaches a of f of x to the n is equal to the limit as x approaches a of f of x to the n. So this is essentially the same thing as this up here, just you'll have like n times as many, like g of x is f of x, like n times. But the cool thing here is that n can be any real number. At least that's what Paul's online note says. But again, be careful, because if you have, let's say you had the limit as x approaches 0 of x to the 1/2. We saw like a couple minutes ago that this does not exist, but this basically tells you that this is equal to the limit as x approaches 0 of x to the 1/2. That's what this property is telling you. But that's wrong, because then you get that this is equal to 0 when in reality it does not exist. So that's why limits can be kind of like finicky and weird. You just have to kind of use your intuition and judgment and go by, always the best thing you can do with limits is plugging in values close to the value on the left hand and right hand side and see what value that approaches. If you're ever stuck, that's the best way you can solve any limit question, because that is essentially how a limit is defined and what it is. So even if this limit property might be true, make sure you remember this caveat for example, like square root of x and others. Okay, let's do a couple of examples. Let's do the limit as x approaches 1 of 3x squared plus 4x, the limit as x approaches pi over 2 of x squared sine of x, and the limit as x approaches 27 of the cube root of x cubed plus, actually, let me do it like, sorry, let's do this. So I'll give you guys like a minute and then I'll explain them, or like ask one of you guys to explain it and then come back. Okay. Yeah, sorry, that's pi over 2. Sorry, my handwriting is the best. Does anyone need more time? Okay. I'm just gonna go over this, and yeah. So here, this is the first property that we saw of limits, which is essentially that you can distribute inside of the over like constants and stuff like that. So this is equal to 3 times the limit as x approaches 1 of x squared plus 4 times the limit as x approaches 1 of x. So this is just 1, this is just 1, so this is 7. Here this is the second limit property that we saw. So we can essentially just split this up into two products. So the limit as x approaches pi over 2, sorry about that again, of x squared times the limit as x approaches pi over 2 of sine of x. So again, here you can just plug it in, because remember, if a function is continuous at like a certain value, usually you can just like plug it in and you'll get a limit. what happens is when it starts to get discontinuous and indeterminate forms and stuff like that is when we have to use more advanced techniques. So right now this might seem like really trivial. We're just like plugging in values into a function, but I promise it gets a little bit more like interesting and stuff like that. So here, pi over 2 squared, the whole thing squared is pi squared over 4 times sine of pi over 2 is 1. This is equal to pi squared over 4. Here we can pass this x equals 7 into that cube root. So this is just the cube root of the limit as x approaches 7 of x plus 1, which is just cube root of 8, which is just 2. So I hope you guys all got those answers. So now we can move on to something that's a little less trivial and more like actual you might need and see in FAMAT. So we're going to talk about limits and infinity. So let's start with if we try to think about what's the limit, if we try to think about what the limit as x approaches 0 of 1 over x is. The graph of that looks something like this. So does anyone have any ideas about what they think this limit is? You can just put it in the chat. Or like you can like unmute and say something. Yeah, so I got one person that said it does not exist, which is correct. Yeah. So your intuition is correct. Like they go to different numbers. Like one goes up to positive infinity and the other goes down to negative infinity. Yeah. So we say that this does not exist. But what we can define in some sense is the limit as x approaches 0 from the positive side. This is equal to positive infinity because as you get smaller and smaller values of x and you're approaching it from the positive side, it's going to be positive infinity. And similarly, we can say that as x approaches 1 over x from the negative side and approaches negative infinity, because you're plugging in smaller values that are negative, so it goes to negative infinity. And so other things that you should watch out for when you're dealing with these limits that like have infinity in them is, for example, the limit as x approaches 0 of ln of x does not exist, because if you look at the graph of ln of x, it looks something like this. And so there's nothing here, like it can't, there's no like graph for it to have a value even. So this does not exist, but we can define a limit from the right hand side, and that's going to be negative infinity. So other graphs that have a sort of like discontinuous behavior is like secant of x, cosecant of x, tangent of x, and like graphs like that. And so that's limits that approach infinity. Now we want to see what happens if our x value approaches infinity. And so maybe you guys have already seen asymptotes in algebra 2 and pre-calc, but this time we're going to go into that, and then we're going to try to generalize that to functions that aren't necessarily polynomials. So let's consider the polynomial x to the 9th plus x to the 7th plus x to the 6th plus 2 over x to the 10th plus x cubed plus x squared plus 1, and the limit as x approaches infinity. So in this scenario, whenever there's a polynomial or any sort of function that you can just like so any function with powers of x, even if it's like what's it called, like a square root or a cube root, what I always like to do is divide by the highest power of x. So here the highest power of x is the 10th, like x to the 10th power, and divide all the coefficients here by all the values by x to the 10th on the top and bottom. So what you get is 1 over x plus 1 over x cubed plus 1 over x to the 4th plus 2 over x to the 10th, all over 1 plus 1 over x to the 7th plus 1 over x to the 8th plus 1 over x to the 10th. Now we can just plug in the limit as x approaches infinity into this expression, and you can very obviously see that if it's 1 over x anything, then it's just going to go to 0. So for example, like 1 over infinity is 0, right? So the same way, like 1 over infinity cubed is also going to be 0. So again, just plugging in isn't always the best way to solve limits, but it's the best way to get started, because then you know which route you're going to take. And so here you can plug in infinity, and then you'll get that all the top is just 0, and on the bottom you have 1 plus 0, so this is just 0. Sorry, 1. Yeah, 0. But what happens now, for example, if we have this limit? Square root of 3x squared plus 1 over 2x plus 2. Here, it's not so obvious that this will have an asymptote. But again, what I like to do is divide by x here, divide by the highest power of x, and then plug in infinity. So the highest power of x here is 1, because if you were to take, you might think it's x squared, but factor in that what's it called, a square root. So that's kind of like a 1/2 power inside of that. So what you can do is like that x squared, you raise that to 1/2 power, it's x. So now you divide the top and bottom by x. So this is going to be 3 plus 1 over x squared over 2 plus 2 over x. And so now as you take the limit as x approaches infinity, you can plug in infinity into the top and bottom, and you'll just get rad 3 over 2, because the 1 over x squared approaches 0 as x goes to infinity, and the 2 over x approaches 0 as x goes to infinity. So that's just rad 3 over 2. One thing to watch out, which is kind of really annoying, but FAMAT writers always love to do this, where they'll have something like this. But what they'll do is they'll put like an x to the 10th term here. So instead of being in like the normal order we're used to seeing it, the x to the 10th is here. And then it just trips you up, because they'll always have like 0 as an answer choice, but the answer choice is actually 1. The answer is actually 1, because there's an x to the 10th term later in the polynomial. So it doesn't change the limit if it's later in the polynomial. It's just they like to put it there to like trip you up and like make sure you're reading carefully, I guess. Okay, so that was polynomials and asymptotes of polynomials, which maybe you've seen before, but now we're going to get into functions that aren't necessarily polynomials. So we're going to talk about something called growth rate. And basically what that is certain functions grow faster than others. So for example, if I were to plug in 2 into x squared versus e to the x, it'll be 4 and e squared. E squared is approximately like what, like 8. But as you go on farther and farther towards infinity, like an exponential function is going to grow faster than a polynomial. So for example, an exponential function might look something like that, whereas a polynomial will look like something like that. So if you plug in, for example, like again, x equals 4, this function's all the way up here. So we can say that an exponential function grows faster than a polynomial. And there's like a sort of hierarchy to this. So x to the x grows faster than x factorial, which grows faster than e to the x, which grows faster than x to the n, which grows faster than log of x. So basically, if you were to graph all of these functions, you'll see x to the x shoot up first, then x factorial, then e to the x, then x to the n, and then log of x. And so also an important distinction to make. So sorry. Yeah. Also, something kind of interesting about the factorial is that you can kind of approximate its growth rate using all the functions we see here. And so basically we say that the n factorial approaches the square root of 2 pi n times n to the e over n. So this is called Stirling's approximation. This is something you definitely won't need for AP Calc, but it's useful to remember when you're thinking about how fast each of these functions grow, and this often shows up in limit problems. So again, so all this basically means is that if you were to take the limit as n approaches infinity of n factorial over like this monstrous expression 2 pi n times n to the e over n, this is just equal to 1. So as you go to infinity, they grow at the same rate. And this is often like a lot of problems, like especially the harder problems you'll see in FAMAT, it'll be like trivial if you know Stirling's approximation, but otherwise there'll be like some complex limit. So this is something that like it's good to keep in mind because it also tells you how to remember the factorials. Also, something you might be thinking is factorials are only defined for natural numbers, right? Like you can only plug in like 1 factorial, 2 factorial. Like how is it on a spectrum of also continuous functions? That's like a whole rabbit hole that I don't really want to get that too into, but it's this thing that if you want to look into, it's called analytic continuation. Basically, what really smart people, way smarter than me, did was they took all the values for factorial, plotted it, and then found some graph that fit through all of these points, and we call it the gamma function. So gamma of x is equal to x minus 1 factorial for integer x. Sorry, for positive integer x. And then it's also defined over, it's like continuous over the real numbers. So it has values for even like decimals. Like you can plug in gamma of 1/2 and you'll get a value. So yeah, I'm not going to get too into it because it's kind of beyond the scope of what we're doing here right now. So now let's get into like actually evaluating limits. So basically your first step whenever you are solving a limit is to plug in f of x. So if you're trying to solve the limit as x approaches a of f of x, you want to plug in a, see what f of a gives you. But before you do that, I want you to be very conscientious about what the graph is. Again, the best way to do limit problems is to think about the graph and see which values they approach. But oftentimes you'll have like really monstrous expressions that you don't really know the graph of. And so the best first step is also plug in x equals a. And then once you do more and more limit problems, you'll know when you have to like think about the graph first, when you have to do other things. But again, the best first step is always plug in f of x equals a. And usually what'll happen is they'll give you an indeterminate form. An indeterminate form basically just means you can't just solve it anymore. You have to somehow manipulate it into a way that's like more easily, like something that we can actually work with. So indeterminate forms, there's I think like 7 of them. It's 0 over 0, infinity over infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, infinity to the 0, and 0 times infinity. So basically, if you plug in x equals a into f of x, and you get one of these indeterminate forms, then it means that you have to do some more manipulation if you want to be able to solve this limit. And so one of the first things we're going to look at is using rational expressions. So this usually happens if your graph is 0 over 0, and it'll look something like the limit as x approaches 2 of x squared minus 5x plus 6 over x minus 2. And so if we plug in 2 into this expression, we'll get 4 minus 10 plus 6 on the top and 2 minus 2 on the bottom, which is 0 over 0. So plugging in x equals a doesn't work. So now we need to think of what to do next. And so if you remember from the very beginning where I had this, this x times x minus 1 over x minus 1, this also gave us an indeterminate form, 0 over 0, right? But we were able to evaluate it by kind of approaching that value from either side. But what we're really doing is like ignoring this x minus 1 term because it technically cancels out. It's just that at x equals 1, it's 0 over 0. But we can cancel it out, and that's why the limit here is equal to 1. So going back to this question, let's see if we can factor the top and get some sort of like factor out the x minus 2 somehow, which because I wrote the problem, obviously you're gonna be able to factor it out. So it's x minus 2 times x minus 3 on the top and x minus 2 on the bottom. And so what we can do is just cancel out the x minus 2 factors on the top and bottom, plug in x equals 2 into this x minus 3 now, and that's just equal to -1. A really, really important distinction to make is that x squared minus 5x plus 6 over x minus 2 is not equal to x minus 3. Because of that one point where it's doesn't exist at x equals 2, that's why they're not equal. But what we can do is when we're evaluating the limit, all we care about is how it approaches from both sides. And that x minus 2 term is essentially negligible in that calculation. So we can cancel it out in order to find our value. But again, it's not equal to that value because they have a point that's different on both graphs. So let's try another one. The limit as x approaches 3 of x cubed minus 4x squared plus x plus 6 over x squared minus x minus 6. So again, the first step is always to plug in x like a. So here let's try plugging in 3. So 3 cubed is 27 minus 4 times 3 squared, which is 4 times 9, which is 36, plus 3 plus 6, all over 9 minus 3 minus 6. So the bottom is equal to 0, and the top is also 0. So again, this is an indeterminate form. Usually, if it has the limit as x approaches 3 of this function, then you know there's going to be an x minus 3 term that you can factor out. So we can do some polynomial long division, x plus 6, and divide that by x minus 3, and we'll get x squared, x cubed minus 3x squared minus x squared plus x minus x minus x plus 3x minus 2x plus 6, and yes, we get minus 2x plus 6, 0. So that's the top. We can factor out. I'm gonna get rid of this. Wait. So on the top we have x minus 3 times x squared minus x minus 2, and then on the bottom, if you factor that, it's x minus 3 times x plus 2. So again, we have this x minus 3 term. We can just cancel that out, and then on the top we have 9 minus 3 minus 2 over 3 plus 2, which is just 4 over 5. So again, if it has a limit as x is approaching a certain value, then first plug in that like value like x equals 3 here. And if it's these rational expressions, usually you can factor out an x equals 3, an x minus 3 term, and then it'll give you something that allows you to get a limit. Next, another way we can evaluate limits is using conjugates. So this will usually happen if you have an infinity minus infinity indeterminate form. And so what does that look like? So if we had the limit as x approaches infinity of the square root of x squared plus 1 minus x. If we were to just plug in infinity here, we would get infinity minus infinity, right? So that's like that indeterminate form where now we need to do something else to manipulate this in a way that like it allows us to solve it. So what we're gonna do is we're gonna multiply by the conjugate. The conjugate is just, for those of you that don't know, a conjugate is just like this but positive, and that allows us to use the difference of squares, which basically says x plus y times x minus y is equal to x squared minus y squared. And you can extend this also to cube roots and fourth roots and so on and so forth. There's a version of this formula in like for every power of n. So for example, x cubed minus y cubed, for those of you that don't know the difference of cubes, it's x plus y, sorry, x minus y times x squared plus xy plus y squared. So as you can see, calculus again is very, very algebra intensive. Like that's why even from what I've seen and everything else, the people that struggle with calculus the most are the people that don't have their algebra down pat. So in order to be successful in calculus, you really, really need to make sure you like know all of these like formulas, you know how to polynomial long divide, you know your trig very well. That's what allows you to be eventually successful in calculus. So anyway, continuing on, we can multiply this by a conjugate minus x. And in order for it to like still be equal to itself, we have to do it as a fraction. So we do this on the top plus x, but also divide again by square root of x squared plus 1 plus x. And remember that like if you're dividing by the same thing, it's just 1. So we're basically multiplying it by 1. But when we multiply the conjugate, what we get is x squared plus 1 minus x squared all over square root of x squared plus 1 plus x. And so these x squareds cancel, and we get 1 over the square root of x squared plus 1 plus x. And so if we take the limit as x approaches infinity, essentially we have 1 over infinity, which is just 0. Another example we have is that the limit as x approaches infinity of x squared plus 3x minus 1 minus x squared plus 2x minus 5. And so again, we can multiply by the conjugate, which is just this, but with a plus on the top and bottom. So x squared plus 3x minus 1 plus x squared plus 2x minus 5 all over x squared plus 3x minus 1 plus x squared plus 2x minus 5. And if we cancel out the terms, if we expand and cancel, we'll get x squared plus 3x minus 1 minus x squared minus 2x plus 5 all over x squared plus 3x minus 1 plus x squared plus 2x minus 5. So these x squareds cancel, and we're left with x plus 4 on the top, and then x squared plus 3x minus 1 on the bottom. Sorry, x squared plus 3x minus 1 squared root of x squared plus 3x minus 1 plus the square root of x squared plus 2x minus 5. And then here again, we divide by the highest power of x, which is just x. So that's 1 plus 4 over x over, on the bottom, you're going to have 1 plus 3 over x, blah, 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 plus 1 plus 2 over x, blah, 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 blah. Again, after a certain, like, we don't care about those terms because we know that they're going to go to 0. So all we have is 1 over, this goes to 0, this goes to 0, this goes to 0, all the dots go to 0. And so it's just 1 over 2, so 1/2. That's conjugates. Now, there's a way you can evaluate limits using the natural logarithm. And then that usually happens when the indeterminate form is something like 1 to the infinity, 0 to the 0, or infinity to the 0. I'm gonna use 2 different techniques in this that are new just to illustrate a point, because it's a little bit difficult to find like limits that are like this, and also I made this a little bit last minute, so I couldn't really find problems. But let's try to evaluate the limit of x to the x as x approaches 0. And so if we plug in x equals 0, we get 0 to the 0 here. So that's one of our indeterminate forms. But what we can do is we can say that this L, we can say that the limit is equal to some L. That's the limit as x approaches 0 plus 0 from the positive side of x to the x. We can then take the ln of both sides. So we have ln of L is equal to the limit as x approaches 0 of x times ln of x. And now what we're going to do is we're going to use a different technique called substitution, which basically says that if we don't like this 0 here, we can turn it into something else. Because if we were to plug in this 0 right here, we're going to get 0 times infinity, because the limit as x approaches 0 of x is just 0, but the limit as x approaches 0 of ln of x is infinity. So we can't evaluate this just yet. But we can say instead that we want to evaluate the limit as, we say that we can define some new variable, let's say y, that's equal to 1 over x. So then this limit is equal to 1 over y times ln of 1 over y. But if x is going to 0 here from the positive side, then y is going to be going to positive infinity. And so that's just what's it called? So basically what I did here was the limit as x approaches 0 from the positive side of 1 over x. That's equal to positive infinity. So I know that the limit as x approaches 0, as x approaches 0 from the positive side, y approaches infinity. And so I can make this substitution here. And then this is equal to the limit as y approaches infinity of negative ln of y over y. That's because ln of 1 over y is just negative ln of y. And from here, what we can do is we can go back to our our growth, growth hierarchy. And we can see that x to the n always grows faster than log of x. And so what that essentially means is the limit as x approaches infinity of log of x over x to the n is always going to be equal to 0, no matter what power of n you have. And so that comes in really handy here, because we can just say that this is equal to 0 because we have the limit as y is approaching infinity. But remember that ln of our limit is equal to 0. So in order to solve for our final limit, we have to raise 0 to the e to the 0, which is just 1. So we got that this limit is equal to 1. So that's like a lot, but that was using two techniques, using substitution and using ln of x. Okay, so now I'm going to go into a little bit more advanced techniques that usually you'll have to have at least 1 year of calculus, or you have to have gone through a calculus course at least once to understand a little bit. But they show up often enough that you should definitely know this. And even if you don't understand this now, maybe take notes on it and look at it in a couple months when you understand all of it. But these show up a lot, and you should know these. So the first is L'Hopital's rule. This is how you're going to solve 90% of limits in FAMAT. Half the time, I don't even think that I'm using L'Hopital's rule, and I realize I am. So actually, I want to say 90, 50% of limits in FAMAT usually use L'Hopital's rule. And for those of you that it's your first time doing calculus, you'll understand this more once you understand derivatives. But basically what we can do is, if the limit as x approaches a of f of x over g of x is equal to 0 over 0, then we can say that this limit will be equal to the limit as x approaches a of f prime of x over g prime of x. And this is surprisingly really, really powerful, because what we can do then is that for example, if we want to solve the limit as x approaches 0 of sine of x over x, then if we were to just plug in 0, then we get this is equal to 0 over 0, which means it's an indeterminate form, like we can't solve it. Also, sorry, so if the limit as x approaches a, the f of x over g of x is equal to 0 over 0 or infinity over infinity. One really, really important distinction to make is that it has to be equal to these indeterminate forms for you to apply this rule, because otherwise it will not work and you'll get the wrong answer. Usually, sometimes the authors also have like a trap answer that expects you to that assumes that you use L'Hopital's rule incorrectly. So here we can use L'Hopital's rule because it's 0 over 0. So we can take the derivative of the top and bottom, and we get cosine of x over 1. So this is just equal to the limit as x approaches 0 of cosine of x over 1, which is just 1 over 1, which is just 1. I'm going to do a little bit of a complicated example. Even if you don't understand L'Hopital's rule, you need to know this formula. So I'm going to derive this formula and just write this down, and maybe you'll understand how to like derive it later if you don't know all of calculus yet. So we're going to try to prove that 1 plus a over n to the bn, the limit as n approaches infinity, this is equal to e to the ab. So we start by saying this L, like again, L, this limit is equal to some L. So the limit as n approaches infinity of 1 plus a to the n, b to the n. So we can take the ln of both sides. So ln of L is equal to the limit as n approaches infinity of ln of, b to the n times ln of 1 plus a over n. Oh, also one important thing I forgot to mention is that you can pass the ln. So if you were to take ln of both sides here, you might think that this is kind of awkward because you have like the limit inside of the ln, but you can pass any continuous function through that limit as long as it's continuous. That's the main caveat. So in this case, because ln is continuous and smooth, we can just pass that in and we can take the ln of that expression. So once we're here, what we can do is the limit as, we can rewrite this as the limit as n approaches infinity of ln of 1 plus a over n over 1 over bn. So this is just the same thing as the one above, but what this allows us to do now is if we plug in n equals infinity, the top is ln of 1, and the bottom is 1 over infinity. So this is just 0 over 0, which lets us use L'Hopital's rule. So we can take the derivative of the top and bottom, and the derivative of the top is 1 over 1 plus a over n times the derivative of 1 plus a over n, which is negative a over n squared. And then the bottom is negative 1 over bn squared. And then we rearrange this and rewrite this. The n squareds cancel, the b comes to the top. So you have the limit as n approaches infinity of ab over 1 plus a over n. And again, you just plug in n equals infinity into that a over n. This is just equal to ab. Remember, ln of our limit is equal to ab. So we can say that L is equal to e to the ab. So even if you didn't understand this, make sure you memorize this formula, because it's going to be the trick to solving a lot of questions really quickly on FAMAT, because it shows up a lot. This one is even a step more that I'm assuming if you're here, you probably don't know this, but it shows up like an annoyingly often amount of times. And so it's really important that you learn it. It's using series to evaluate limits. So actually, maybe some of you have seen in pre-calc that, actually, I'm gonna start by saying that those of you that have seen in, this is the formula. The limit as n approaches infinity of 1 plus a over n to the bn is equal to e to the ab. So, for those of you that remember series from Algebra 2 and pre-calc, we were mainly working with arithmetic series and geometric series. And so, sorry, I'm going to scroll down now. Is that okay? Okay, cool. So if you remember from algebra 2, we said that the sum of x to the n from n equals 0 to infinity is equal to 1 over 1 minus x. So we call this like a power series, and this is like a whole separate topic in calculus, but all I'm going to say is that there's a power series for every function that you can think of. And so the one that I'm going to be using right now is that x to the n over n factorial is equal to e to the x. And so just take my word for granted right now. You'll learn how this works like a lot later. But the sum from n equals 0 to infinity of x to the n over n factorial is equal to e to the x. This is called a Taylor series. But we can use this to evaluate limits, because let's say we have e to the x minus 1 minus x squared over 2 minus x squared over 3 over 6, all over x to the fourth. And we want the limit as x approaches 0. Now, if we were to plug x equals 0 into this, we would get on the bottom 0 to the fourth is 0, and 1 minus 1 minus 0 minus 0 minus 0. So it's 0 over 0. So it's an indeterminate form. So what we can do in this scenario is use the series for e to the x to solve this limit. So the series for e to the x is 1 plus x squared over 2 plus x to the 3 over 6 plus x to the 4 over 24, so on and so forth, because 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, so on and so forth. And if we subtract that from this on the top, we'll get x to the 4th to the 24th plus x to the 5th over 5 factorial, so on and so forth. And on the bottom, all we have is x to the 4th. Now, when we divide x to the 4th on the top and bottom, also sorry, these are horrible x's. Now, when we divide x to the 4th on the top and bottom, we'll get 1 over 24 plus x over 5 factorial, so on and so forth. But we're taking this as the limit of x approaches 0. So all of these values after this are just going to be higher and higher powers of x. So x squared, x cubed. I don't really care what their coefficients are, because when you plug in x equals 0, they're all going to go to 0. They're all going to cancel. So this is just equal to 1 over 24. So again, this is only more useful when you know more Taylor series. Right now, the only Taylor series I kind of want to give you is e to the x, because if I give you too much, then it'll be like overwhelming. Already, this is probably kind of overwhelming. But if you want to look more into it, you can look up Taylor series, and those are used pretty commonly to solve limits. And it's important to keep in mind, because especially when you get to like states and topic tests especially, they'll have these limits using series to solve them. Okay, so a couple more things before like we finish up. I'm going to talk about continuity. So I've been throwing this word continuity around a lot, and maybe you've heard it in pre-calculus or something, but let's actually like formally rigorously define what continuity means. So we say that a function is continuous at a. Yes, it did start an hour ago. Sorry. So a function f of x is continuous. I recorded a lot of it though. I forgot to record like the first 10 minutes. So if you missed a little bit, then we'll send the link out and you'll be able to watch it later. But yeah, so a function f of x is continuous at x equals a if the limit as x approaches a of f of x is equal to f of a. So some examples to start off with. For example, at the beginning we had f of x equals x, and we were seeing what the limit was as you approach 1. So this is obviously continuous at 1, because the limit as x approaches 1 of f of x equals x is just 1, and similarly f of 1 is 1. And so since the limit is equal to the function itself, you can say f of x equals x is continuous at 1. Some non-examples would be the x times x minus 1 over x minus 1, because even though the limit exists at x equals 1, the function does not. So the limit as x approaches 1 of x over x minus 1 over x minus 1 is 1. But f of sorry, if this is f of x, but f of 1 is undefined. So f of x is not continuous at x equals 1. Okay, so common questions that show up in FAMAT is that they'll give you some piecewise function f of x that's x squared plus 2 for x less than 0 and a minus x for x greater than or equal to 0. So, and they'll ask you for what value of a is f of x continuous for all real numbers. And so we have to find the limit as x approaches, usually the discontinuity, as long as there's no discontinuity within these functions themselves, the discontinuity will occur at this value. So we want to find the limit as x approaches 0 of f of x. So again, a limit only exists if it exists from the left-hand side and the right-hand side. So from the left-hand side, this is equivalent to the limit as x approaches 0 of x squared plus 2, which is just 2. Similarly, the limit as x approaches 0 from the right-hand side is equivalent to the limit as x approaches 0 from the right-hand side of a minus x. Also, what value of a? F of x continuous. Okay. So if we plug in 0 here, we get that this is equal to a. And so in order for this limit to exist, the limit needs to be equal to each other from the left-hand side and the right-hand side. So this just gives us like trivially a equals 2. So for a equals 2, this function is continuous for all values of x. So this is like a pretty basic example, but it gets a little bit more complicated. You'll have like multiple functions. It'll be like 3 or 4 different functions, and it'll be a bit more complicated. But this is the idea. But one last thing to check again is that f of 0 has to be equal to the limit. So the limit is 2. But we see that f of x it's equal to a minus x for x greater than or equal to 0. So we can just plug it into 2 minus 0, which is just 2. So we can say that it's continuous at 2. One last thing I'm going to go over that you don't really need to understand, but it's just shows up and it's really annoying because it shows up and I don't like it. But it's called the epsilon delta definition for limits. And so basically, right now, our approach to limits has been kind of like wishy-washy, like very intuitive and not very rigorous. And so we're just saying like as it approaches, but like what does that even mean? So this basically tries to formalize a definition for limits. So this again, you'll never see this in your calculus class probably, but it shows up on FAMAT sometimes. And they'll literally ask you what is the epsilon delta definition for limits using like symbols. And so I'll write the epsilon delta definition down and then give you an example. So let f of x be a function defined on an interval that contains x equals a. But an important distinction to make is that f of a can be undefined. F of x just has to be defined on an interval that contains x equals a. And we are trying to prove that the limit as x approaches a of f of x is equal to L. So also one thing to keep in mind is that proving stuff is very different than solving for stuff. So especially as you get into like higher level math, and maybe you take like a proofs class or something like that, oftentimes the question is literally prove that this is true. Like they already give you the answer, but you need to like do the actual proof, which is the actual groundwork. So if you're trying to prove this epsilon delta definition, then you already need to know the limit. So that's an important distinction to make. And the statement is for all epsilon greater than 0, there exists some delta greater than 0 such that for all x, the absolute value x f of x minus L is less than epsilon when 0 is less than x minus a, x minus a is less than delta. So this is just like a bunch of word garbage, like it doesn't mean anything. But basically what it's trying to say is that if we know that f of x is the limit as x approaches a of f of x is equal to some L, then that will be bounded as you get closer and closer to that value of a. And so the best way to do this is like to show it in an example. So for example, prove that the limit as x approaches 2 of 2x minus 2 is equal to 2. So we know that the limit is equal to 2. So what we can do is we can plug in f of x and L into here. So 2x minus 2 minus L, which is 2, is less than epsilon. And we need to find some delta such that like this is true. So ideally we need like some expression with absolute value of x minus a in there. So what we can do is rewrite this as 2x minus 4 less than epsilon. And then we can pull out a 2. This is 2 times x minus 4. Sorry, x minus 2 is less than epsilon. And then therefore, the absolute value of x minus 2 is less than epsilon over 2. And it's always going to be less than 0. Always going to be greater than 0 because it's absolute value. And remember again that we're approaching a, we're not equal to a. And so this doesn't need to be less than or equal to, less than or equal to. So it's not going to be less than or equal to, it's just going to be less than. So we have this expression. We found some delta such that for all of x, this statement is true. And again, this might seem like this took me a couple of passes to like properly understand. Even I don't understand it very well now, but this shows up sometimes on FAMATs. Usually they'll give you a definition, so it'll be a refresher on the actual test. But it's a good thing to like keep in mind and know when you take FAMAT tests. So, oh yeah, I also wanted to say for sometimes like one test I saw, they wrote this in using like math speak or math symbols. And so this is a symbol for all. And then this is the symbol there exists. And so sometimes you'll see this statement written as for all epsilon greater than 0, there exists some so delta greater than 0. And then you'll often see such that abbreviated as s dot t, such that for all x, f of absolute value of f of x minus L is less than epsilon when 0 is less than absolute value of x minus a is less than delta. So yeah, so make sure you know these symbols, and it's honestly better to if you were to memorize this, it's honestly better to memorize this and the symbols independently, and then just be able to apply it to whenever you see them in the on a test or something. that's all I had, like lessons as far as lessons go for today. This is probably a lot, especially if you're doing calculus for the first time. I'm really sorry. I feel like one of the problems about having this at like the beginning of the year is like it's kind of hard to do calculus problems, especially when you don't know calculus. And so hopefully, even if you didn't understand anything, it's still some sort of exposure that you can take into your AP Calc class. And if you see, for example, some epsilon delta thing, you can be like, oh, I saw that at the problem party or whatever. And so really quickly before I'm going to open it up to questions, because I'm sure you probably have a lot. So what to do after this? Can we do some limits and derivation problems? Yeah. So first I'm going to go over stuff that you can do after this lecture, and then I'll go into more problems and opening up to questions. So if you're new to calc, make sure you know pre-calc, because again, calculus is like 80% pre-calc and algebra, 20% actual calculus. So no pre-calc. And again, those resources that you can use to learn this is Paul's online notes. He has a specific section in his Calc 1 lecture series where he specifically goes over the pre-calc you need to know for calculus. And so that's really good if you want to review. You can also go through, again, Khan Academy. I have this written at the top. And of course, past FAMATs will get you acquainted with the pre-calc knowledge you need to know for FAMAT Calc. If you're really, really confident on your pre-calc and you want to get a head start on limits and stuff like that, again, Paul's online notes. I can't stress how good of a resource this is, because he has a lot of really good basic problems that still require you to like, it make sure you know like how to go through all the motions of actually evaluating limits and stuff like that. So notes for limits. So I kind of like rushed through a lot of the different ways you can solve limits, and he will give you like a really good in-depth like how to solve these limits. And you can click on practice problems at the top, and he'll give you like 4 to 5 different practice problems, and he'll give you solutions for those. And so those will really help you like solidify and understand how you can solve limits. And you can try attempting the problem set, but I'm gonna warn you guys like right now, if you're new to calc, it might be a little bit difficult. I kind of aim this towards people who are a little bit like 1 year into calc, because it's because I didn't want them to get bored during the lecture. Also, I think a lot of people joined, so I'm gonna drop the problem set in the chat again. Let's see. Sorry. This is the problem set, and then these are the hints. And again, I'll try to get solutions up by the end of the week, and I'll send it out to you guys. And if you have any questions, you can email to me at this, or you can just message me on Discord, or like there's like, yeah. I think I'm also up on the FAMAT Delegates website, so you can find my email there and contact me and ask me any questions. Again, I'm Srijan Deoraj, if you don't know who I am. So you can attempt the problem set. And then also, if you still want to learn more, you can go in and go through more of Paul's online notes, go through Khan Academy, and those give you like really solid foundational skills that let you attempt more of the FAMAT calculus. If you aren't new to calc, do the problem set. Do FAMATs. If you haven't taken BC yet, I would suggest you get a head start on learning series, parametric, and polar, because especially if your teacher is just going to go over AB for the first chunk of the year, it might be a little bit like boring and annoying. So maybe you can get a head start on that. Also some cool non-FAMAT limit stuff. Paul's on my notes for limits in 3D. And so what's really cool is you can extend this idea of getting closer and closer on both sides to getting closer and closer, like as a circle approaches a certain value, like as the radius goes to 0, because once you go into multiple dimensions, it's hard to like just say going from either side. And so I thought that was kind of cool when I read about it. So if you want to, you can read up on that. Also, if you're like really, really ambitious, you can look into metric spaces and real analysis. This is like very, very like math major proof heavy stuff, but like it's formalizing a lot of the stuff we learn in calculus into formalizing it, and so that like you can actually prove a lot of things that we kind of just take for granted in calculus. And yeah, so someone asked if we know everything up to integration, should we be okay for FAMAT given more time? Yes, I would just say that especially like the March regionals and states tests, they usually incorporate more series and polar and parametric. And honestly, if you've gone up to integration and you know it well, you've gone through like 90% of calc. Series, parametric, and polar is just like something that like it's not that hard to learn on your own, and you can if you want to. And then by then you'll know like everything you know for calc. Do you have problem sets for derivatives and integrals in series? No, not yet, but hopefully in the coming months I will. I can give you, for example, the best resource you have is past FAMATs. Those are going to be the best representation for FAMATs that are going to be written in the future. So for derivatives, I would say go to the limits and derivatives test. The past 2 years have been relatively difficult, which means that the state's limits and derivatives tests, and since they've been difficult, that means they have good problems, which you can learn from, and that's like the best way to do it. Integrals, I can send you the integration V from last year, which really taught me a lot about integration. But if you don't know like a lot of the advanced techniques for integrals, they're kind of like difficult, and there's like a really, really high barrier to entry. And for series, again, sequence and series, like states tests is where I learned most of the knowledge I have about sequence and series. But if you give me like a lot of time, then I will get you problem sets. What do you mean by advanced techniques? So for integrals, we'll get into this later if we keep doing this. You have your regular U substitution and stuff like that, but then you also have, if you know, for example, integration by parts, then there's trig substitution, then you have to know how to do trig integrals, then you have to know how to do, for example, there's Weierstrass substitution, then you have to learn there's like more advanced techniques like Feynman's technique and something like that. Can you please send me the integration V file? Yeah, I'll actually put that as a note for myself. Integration V. I'll send it out as like an announcement on Discord, maybe later if someone gives me admin on Discord. But yeah. Besides that, does anyone have any questions? Does anyone have any questions? Can you send Discord link? Oh, is Dunmay here? No, he left.
Yes, I am here. I got it.
Oh yeah, can you send the Discord link in the chat?
Yeah, give me a second.
Okay, does anyone have any questions on limits and like any of like, you can ask like what is the limit again? I won't be offended, I promise. I know I went through it kind of quickly, but yeah. If no one has any questions, where can I get more past FAMAT sets since the FAMAT? So there's a couple resources right now. Well, two main resources. There's the Deoraj. If you scroll up on Discord announcements, you'll see the Deoraj website for FAMATs. Also, there's a Google Drive folder with all the states tests. I'm not sure if it's been shared on the Discord, but if it's not shared, it'll be there by the end of the week. Let me add that as well. States tests. And the Doral stuff only has the regionals and stuff. How can you ask questions on Discord? So there's a lot of different channels, like you have Mu Alpha Theta. You can ask it there first. If you don't get a response there, you can email me. If I don't respond because I'm notorious at like not checking any of my messages, then you can ask like Sharva, Kamal, Tanmay, and then they can probably help you out. Or yeah, or you can just ask
a great starting point is if you have like a general question just about like competitions or something, you can ask it in the Mayo general chat. And then if you have an actual math question, you can ask in the Mu chat. And then there's a bunch of smart people in that server, and they'll respond to you.
Yeah. Does anyone have any other questions? I don't have perms. Oh yeah, follow at FAMAT students on.
Yes,
Instagram.
Jamal's notorious about this, but make sure everyone follows FAMAT students on Instagram.
Also, sorry this was like so lecture heavy. Next time, if you like have more problems, I'll go over those first. And also, like next time, hopefully we'll also like know calculus, so we could actually do calculus problems instead of just like lecturing the entire time. But yeah, so maybe next time it won't be so much like this is what a limit is, but I'll try to teach you more like, oh, this is the stuff that like FAMAT specifically asks for and stuff that like you need to know for FAMAT. Yeah.
Yeah, so the plan is to have basically a session every month, but so like report to your sponsors if they care about this, that you like the session if you did, because then we're more likely to have these again. And if you're like really interested in like teaching one of these, like if you feel like you know how to do FAMAT problems really well and you want to help out, that's also something you can message us about. Yeah, follow the socials, join the Discord, do everything like that. I can't think of anything else to add.
Something Amal brought up earlier is that if you're rich, you can give us money and we can do more events like these. I'm joking.
If you do have funds, we
Definitely need funds.
we'd like to sponsor scholarships in the end of the year. That's a good point for everyone here. If you're graduating senior, there's going to be scholarships at the end of the year that you should definitely apply for. And in an essay where you have to write about your involvement in FAMAT, you can say you came to these sessions. So yeah, that's what we need the funds for. If mommy or daddy has some money, just let us know. I'm just kidding. But we're fundraising right now. You should add us on Amazon Smiles.
Yeah, also I'm gonna send the link to the initial sign-in form, and you guys can edit your response and like put any questions or comments that you had, just so that we can know if you guys like would have preferred that it ran a different way, or like anything specific that we could have done to make your experience better.
Oh yeah,
that way we can have a better meeting in September.
Yeah, you guys can like rip on me. Like I won't be offended, I promise. Like if you're like, oh, you went super fast, I didn't understand anything. The next time, like I'll try to make it go a little bit slower. But yeah. When will the recording be posted? That's a great question. As soon as possible, probably. I think in order for us to have the recording file, the Zoom meeting needs to end. And once that, it'll probably take a while to upload to Google Drive. But we'll try to create like a shared Google Drive folder where, yeah, we'll post it in the Discord. Don't worry about it. It'll be a shared Google Drive. Have like everything.
So we're gonna make a Google Drive for it, and we might put it on YouTube, maybe. We'll see how that goes.
Yeah.
But we will email it to you on the email that you provided in the form. So yeah.
Okay. I don't really have anything else for you guys. If you have any questions, you can stick around if you don't want to ask it in front of anyone else. or you can just direct message me. Besides that, it's, will you teach us complex analysis? I don't know complex analysis. I wish I knew complex analysis. There are a surprising, I don't think it shows up, but there are some like residue theorem integrals that are just like, oh, does this converge? And I don't know, but complex analysis is cool. The only thing I know about complex analysis is residue theorem, like vaguely. So yeah, I found this, okay. Thank you so much. I really appreciate it.
All right, thank you guys for coming out. On that note, we're ending it. So just if you scroll up a little bit in the chat, feel free to give us some feedback on how we can do it better. Yeah, I'm gonna leave now, but I'm glad you guys had a good time.
I will not teach you how to solve the Navier-Stokes equations, but maybe someday, what's his face? I'm forgetting. The guy at UC Berkeley or wherever, I don't know, or UCLA. I'm forgetting his name, but maybe he'll eventually teach solve the Navier-Stokes equation. But yeah. Bye.